Hello, and welcome to this recorded e-learning on Basic FPGA Configuration, Part 1. My name is Frank Nelson. I'll be your instructor for this module. This module is intended to introduce you to FPGA configuration so that you can choose the appropriate configuration scheme that best supports your application. Please note that we recommend you listen to the Basic FPGA Configuration 2 recorded e-learning after completing this recorded e-learning module. If you are an experienced ASIC designer or new to FPGA design, this module will help you reduce your learning curve and get productive faster with your new FPGA design. This module will help you understand the configuration process. The configuration principles and configuration modes I'm about to describe apply to virtually all Xilinx devices, except where noted in the recording. This particularly applies to some of the slightly older architectures. After completing this module, you'll be able to describe the FPGA configuration pins. This is essential because the configuration process is relatively automatic after the configuration scheme has been selected, and this is done by pulling the configuration mode pins high or low. You'll also understand the differences between the different configuration schemes that are available to you. From this information, you'll be able to choose an appropriate FPGA configuration scheme. Before choosing a configuration scheme, however, you must know some of the basics and understand the advantages or disadvantages of each scheme. This module is intended to highlight why customers choose one configuration scheme over another. The Basic FPGA Configuration 2 module will introduce you to daisy chains and prototyping hardware that is available to you. It will also answer the most frequently asked questions about the FPGA configuration process. What is configuration? Well, configuration is the process of loading configuration data into your FPGA. This is necessary because the FPGAs are SRAM-based. SRAM cells are not static and lose their programming when they lose power. Unlike flash cells, which are static and never lose their programming unless they complete an erase cycle, FPGAs lose their programming each time they are powered down. This brings to mind the question, why are FPGAs made with SRAM logic and not flash if reprogramming is going to take extra effort and cost? Well, the answer to that is that SRAM cells are much smaller than flash cells, and FPGAs offer much larger densities than CPLDs. So, since we are using a large FPGA then, we need to plan on having a memory component somewhere that can store the FPGA's bit stream. In general, each of the configuration modes supports a variety of configuration methodologies. Keep in mind that FPGAs are designed to offer a wide range of configuration solutions in which some are simpler and need less debugging, and some are less expensive and give you a choice of memory components, and some offer a great deal of flexibility to suit a wide range of applications. In this example, the configuration data source could be at its simplest a flash memory component, or the bitstream could be stored on a network or downloaded from a laptop computer. The control logic shown in this diagram would have to be customized by the user. If the designer did not want to build this extra control logic, there are additional master configuration modes that use dedicated control logic inside of the FPGA to program the FPGA with a bitstream stored on a variety of memory components. The supported memory devices include a Xilinx PROM, a Byte-Wide Peripheral Interface or BPI PROM, or a Serial Peripheral Interface or SPI PROM. Depending on the configuration mode you choose, there are two types of data paths, serial and multi-bit. Serial data paths are used to minimize the number of device pins required. Multi-bit data paths offered include by 8, by 16, and by 32 bit widths. These are used for higher performance or enable access to industry standard interfaces. These multi-bit solutions are ideal for connection to external data sources like processors or parallel flash memories. In the end, every configuration scheme has advantages over another. Some configuration modes are designed for debugging, while others lend themselves to maximizing the system's available memory resources, and still others might give designers a choice of vendors. Choosing a configuration technique just requires the user to understand what their system is going to have and to anticipate what they are going to need their system to do. In some instances, customers build their configuration scheme to include multiple configuration modes, so they can test and debug their system through one configuration scheme and then configure their FPGA through still another scheme after the product has been released. Like processors and processor peripherals, Xilinx FPGAs can be reprogrammed in system, on demand, and an unlimited number of times. In fact, some customers take advantage of the reconfigurable nature of FPGAs to the extent that they have multiple bit streams loaded onto their system. This feature is referred to as multi-boot. Multi-boot can save the cost of purchasing another FPGA or even a larger ASIC. So as I just described, configuration must occur on power up, but can also occur on demand by toggling the FPGA's program B pin. So as I just described, configuration must occur on power up, but can also occur on demand by toggling the FPGA's programming pin. Additionally, configuration can be triggered with commands over the SelectMAP or JTAG ports without having to toggle the program pin. FPGAs need to be configured because their SRAM cells are volatile. The user will have to plan on storing their configuration data in a PROM or some other external data source. To build your system, you'll have to understand the basic configuration process and how to set up various configuration modes and daisy chains. But before you can get to that point, you'll need to understand the advantages and disadvantages of each configuration scheme so you can choose the appropriate mode for your system. Well, there are lots of configuration possibilities to consider. The first we're going to consider is configuring via a Xilinx download cable. These cables allow the user to reconfigure their FPGA with only a download cable and their computer. The configuration modes described are used primarily for prototyping and debugging and design. These cables are low cost and are typically used to configure the FPGA in a JTAG configuration mode. We will discuss the additional hardware available in the basic FPGA Configuration 2 module. Configuration can also occur with the use of a microprocessor or microcontroller. These configuration schemes involve some other external control logic being used to control the configuration process. In these configuration modes, the FPGA is a slave to whatever control logic is managing the configuration. These configuration schemes require extra components and thus have added cost associated with them. Most users consider this configuration scheme if they already have the external control logic available as part of their system. Configuration also can be completed using the Xilinx Platform Flash PROM. These configuration schemes usually use the FPGA's built-in configuration logic to control the FPGA's configuration process. With these components, the FPGA usually configures itself. These configuration schemes require the user to buy a PROM, which has some additional cost, but these schemes are usually the easiest to debug since the control logic is already fixed as part of the FPGA. We will talk about the Xilinx Platform Flash products in the basic FPGA Configuration 2 module. Some new configuration options have just become available to Xilinx users. The Serial Peripheral Interface, or SPI, and the Byte-Wide Peripheral Interface, or BPI, configuration schemes allow users to purchase off-the-shelf commodity flash components. The flash memory can then be used to store the configuration bit stream and for the user's application memory if the user is building an embedded system that would include some software. The configuration mode pins define to the FPGA what configuration scheme is about to be used to program the FPGA. This is important because the FPGA can handle several different schemes, and since each scheme behaves very differently from each other, the FPGA needs to know clearly and precisely what is going to happen next. If a user wanted to build a configuration scheme that included multiple configuration techniques, the first thing the designer would have to do is build the logic to drive the mode pins. There are 3 dedicated mode pins on the FPGA, and their simple binary combination defines the configuration scheme. The configuration pins each have their own purpose. Some are active switches, that is, inputs to the FPGA, while others are status indicators, or outputs. Understanding their roles is the first step if the user is going to debug their own configuration problem. The configuration data stream is a little more complex, but understanding it is important if you are going to debug your own configuration problem. Note that configuration problems usually occur when the user is building a scheme that includes multiple configuration techniques. This is not especially challenging, but is a necessary byproduct of a designer, quote, doing it himself. Specific pins in the FPGA are used during configuration. Some pins act differently depending upon their configuration mode. For example, the clock, or C clock pin, is an output in some modes, while it is an input in other configuration modes. Some pins are only used in specific configuration modes as well. Now, this is a little challenging because each configuration scheme can differ so much. That's because each pin may or may not be used in different configuration techniques. This is why the datasheet and the user guide for each FPGA discusses each configuration scheme in detail. In fact, the user guide covers each configuration technique in more detail than we're going to provide here, so remember to review the section on your chosen configuration scheme. As I mentioned earlier, the mode pins define to the FPGA the mode selected. There are 3 mode pins, and they are inputs to the FPGA. The program pin is an input pin that is active low. It initiates the configuration process. So if you're going to reconfigure the device after it has already been programmed, then you will have to toggle this input pin to start reconfiguration all over again. The clock pin is an input or an output pin depending on your configuration scheme. Note that if it is an output, the clock can run at up to 100 MHz depending on the device you choose, but will default to a much slower rate. If you want to modify the configuration rate, you set the config rate attribute in the BitGen program. So check the configuration user guide if you want to modify this. The init pin has multiple functions. At the start of configuration, init goes low, signaling that the FPGA's memory is being cleared. After clearing, it is released to be pulled high by an external resistor. Later, when the FPGA is loading its bitstream, init can go low, indicating that the bitstream has failed its CRC check, and the configuration is being aborted. The CRC check is a checksum that indicates whether the bitstream has been corrupted. The done pin indicates the completion of the configuration process. It's bidirectional, so the user can delay the startup sequence. After configuring the FPGA, the starting of the FPGA is often controlled by the user to control the releasing of the entire FPGA system to operate. On a side note, in case you don't know, BitGen is the bitstream generation utility included with the ISE software. It is used to create a bitstream from the implemented design and is used for configuring your device. Other important configuration pins are the data in pin, which is used to load in the serial configuration data. The data out pin is used to output the bitstream to the next device in case the user has built a daisy chain of multiple FPGAs into the system. A daisy chain, as we'll see later, is used to save PROMs or other memory components. It allows the user to store the bitstreams of multiple FPGAs in one large memory component. To program multiple FPGAs in this way, the configuration scheme has to be configured to pass the data through each FPGA once it has been programmed. Now we'll talk a little bit more about this configuration later on. Some of the configuration pins are dual-purpose pins. After configuration is complete, they become normal user I/O pins. Users will sometimes prohibit the use of these I/O pins with the pin ahead utility. Check your device's datasheet or configuration user guide to determine which configuration pins are dual purpose. Now, this slide will list all of the currently supported configuration schemes for all of our FPGAs. There are serial and parallel modes. First of all, parallel modes are inherently faster even though they may operate at the same speed since they configure the device a byte at a time. The primary advantages and disadvantages include debugging time, debugging effort, cost, and speed of loading the bitstream. Now, first of all, configuring with JTAG is most frequently used when debugging a design. It is always recommended that customers include a JTAG configuration path so they can debug their design and system. No external control logic is necessary since the FPGA has a built-in JTAG chain and the external control logic is provided by the JTAG cable. Master serial is perhaps the easiest configuration technique to debug. Since the FPGA configures itself, this is the easiest to debug, but requires the user to purchase a serial PROM or a serial flash, such as the Xilinx platform flash. Slave serial mode uses external control logic that the user must design. This control logic has to feed the bitstream to the FPGA from whatever external data source the system has. Many customers store their data in a PROM or other memory resource in this case. SPI configuration mode is new and requires the user to purchase a serial peripheral interface flash PROM. The benefit is that this configuration uses a price-competitive SPI PROM rather than another means to store the bitstream. It is also possible to use the SPI PROM to store software code in case the user is building an embedded application. This is a relatively simple configuration scheme to debug since the control logic is already a part of the FPGA. Now there are several parallel modes which enable faster configuration than serial modes. Master SelectMAP uses FPGA configuration logic to be used and uses a parallel flash, such as the platform flash, to load the data a byte at a time. Slave SelectMAP allows the user to customize their configuration control logic and still load data a byte at a time. Note that Slave SelectMAP also supports a by32 data line implementation when you target vertex 5 or vertex 6. BPI, or Byte-Wide Peripheral Interface mode, supports the use of an industry-standard BPI flash component. It loads the data in parallel, so it is a faster configuration option than using a serial peripheral interface. BPI has the added advantage of allowing the user to store their software code with their configuration bitstream as well. Note that SPI and BPI are supported with Xilinx's newest FPGAs, including Spartan 3E, Spartan 6, Vertex 5, and Vertex 6. So here we have a diagram that describes the JTAG configuration mode. The TCK, TDI, TMS, and TDO pins are the only pins necessary for this configuration mode. All of the JTAG pins are standard and are dedicated on the FPGA. After they are used for configuration, they can be used as I/O pins or be prevented from being used for I/O. As configuration occurs, the bitstream for each device flows serially through each FPGA until the appropriate FPGA receives its programming information. Note that the control signals are each connected in parallel. JTAG access will override any other configuration mode. All the other modes require the mode pins to be set correctly for them and are mutually exclusive thereafter. But JTAG access is always available regardless of the mode pin settings. This is required by the standard and makes debugging much simpler. After the JTAG mode has been identified by the FPGA, the JTAG pins become activated and the JTAG interface is used as a communication channel for the FPGA to be configured. This channel can also be used to create a boundary scan chain. The boundary scan logic is dedicated as part of each Xilinx FPGA and has all the mandatory elements to suit the IEEE standards. The JTAG mode allows the user to easily cascade any number of FPGAs into one chain for programming or debugging. JTAG mode allows a bitstream to be downloaded to each of the FPGAs in a chain with only a programming cable and a 4-pin JTAG header attached to a demo board. Since reconfiguring in this mode does not require any memory components to store the bitstream, this mode is primarily used for debugging and not for the end use of an application. This flow is possible because Xilinx FPGAs are SRAM-based and thus reprogrammable. This means that the user only has to generate a new bitstream with the impact utility and then re-download the new design into the FPGA. While Xilinx does not specify configuration times, downloading with JTAG takes between a few seconds and a couple of minutes. This is done default cable speed and the platform cable USB being used. Now this will vary depending on your PC, FPGA, and as I mentioned, the programming cable you choose. Impact is used for file generation and configuration of Xilinx's FPGAs. The impact utility is included with the ISE tools. It can also be used to program a CPLD or a Xilinx PROM and indirectly program a third-party flash component using the BPI or SPI configuration modes. Xilinx provides a number of programming cables that lend themselves to various purposes. We'll talk more about this again in configuration 2. Just make sure after selecting a suitable cable, you have also planned for an appropriate cable connector to be available on your board. The impact utility programs FPGAs through several parallel cables, including the platform cable USB. In master serial configuration mode, the FPGA provides all the necessary control logic. In this case, since the control logic is fixed, this is one of the easiest configuration schemes to debug. All three mode pins, first of all, are tied low for master serial configuration mode. One of the things you might be wondering is, why master? Well, since the FPGA is providing the control logic and driving the necessary control signals, the FPGA is the master of the system. Unlike slave configuration modes where external control logic is required and the FPGA does not handle configuration of itself. The FPGA generates its own configuration clock in this mode. This clock is then driven outside the FPGA to a serial data source, usually a Xilinx platform flash. In response to the clock, the PROM provides the data 1 bit at a time. The configuration scheme is the slowest in this case of those offered, but is also the easiest to debug. This mode is used when data is stored in a serial PROM. Xilinx offers a variety of platform flash densities to accommodate the case where a designer has a multiple FPGA daisy chain and wants to store all of the FPGA bit streams in one flash device. For more information about this, check your device's datasheet or the user configuration guide. Now, this configuration scheme is the slowest configuration mode, again, but the easiest to debug since the control logic is fixed. In slave serial mode, an external host, such as a microprocessor or microcontroller, writes data serially into the FPGA. Since the clock and the control logic are built by the user outside of the FPGA, it is imperative that the user build a control logic to provide the serial data to the FPGA with sufficient setup time before each rising edge. If you're planning to program multiple FPGAs in a daisy chain, the data out pin will be connected to the data in pin of the next FPGA. The advantage is that the user could store the bit streams for multiple FPGAs in one external memory resource other than a flash PROM, and depending upon the application, this may be beneficial as well as cost effective. Note that this configuration mode is rather slow, only loading data 1 bit per clock. Master SelectMAP, like the other master configuration schemes, has its control logic already included with the FPGA. The difference with this master configuration scheme is that it loads the configuration data 1 byte at a time, even though it is internally serialized. So this mode does not configure any faster than a serial configuration mode. Note that the Xilinx Platform Flash XL is often used with this configuration mode as the data source. The use of the Xilinx Platform Flash XL enables faster configuration times when targeting Vertex 5 and Vertex 6 FPGAs, because it supports BPI or Byte-Wide Peripheral Interface modes. In slave SelectMAP mode, an external host such as a microprocessor or microcontroller will write byte-wide configuration data into the FPGA using a typical peripheral interface. In this mode, the external host starts the configuration process by toggling the program pin and then monitoring that the init pin goes high. This indicates the FPGA is ready to receive its first data. The host asserts the active low chip select signal, that's CSI_B, and the active low write signal, which is read_write_B. The host then continues supplying data and clock signals until either the FPGA's done pin goes high, indicating a successful configuration, or until the FPGA's init B pin goes low, indicating a configuration error. In this mode, data can be provided with 8-bit, 16-bit, or 32-bit data lines when using Vertex 5 or Vertex 6. Note that Spartan 6 only supports 8-bit and 16-bit data line configurations. This configuration mode supports the use of asynchronous peripherals that provide a write strobe, which can be used to have the FPGA generate the 8 clock pulses necessary. This mode also supports a synchronous peripheral interface where the control logic provides the necessary 8 clock pulses per data byte. Note that the Xilinx Platform Flash XL device is often used as the byte-wide data source. In this example, and in that case, no external control logic would be required. This assures the reliability of the configuration scheme's design and reduces your risk and debug time. The Serial Peripheral Interface, or SPI configuration mode, is supported for Vertex 5, Vertex 6, Spartan 3E, and Spartan 6 FPGAs. This configuration mode allows the FPGA to configure itself from an industry standard SPI flash PROM without construction of your own control logic. The FPGA generates a clock signal and drives a command to the PROM. The PROM then responds with the appropriate data. This mode also supports multi-boot applications where additional bit streams can be loaded by the FPGA on command. This data is loaded serially and thus is not a fast configuration scheme. In Vertex FPGAs, the FPGA requires the vendor select signals, that is the VS, which is 3 bits wide. These bits are used by the PROM to determine which vendor's SPI flash PROM is being used and which commands to issue. However, if you're targeting Spartan 6, these signals are not needed since the first command code issued is always recognized. If you're planning on using Spartan 6, note that it also supports 2-bit and 4-bit data lines. The commands for SPI operations are vendor specific, therefore it is useful for you to make sure that you are using a supported SPI flash PROM. However, most devices will use the common commands supported. Check the device datasheet for a list of the currently supported PROMs. Currently, these vendors include Mnemonics, Spansion, Winbond, and Atmel. Users should plan on selecting a flash PROM that has sufficient size to contain the FPGA's entire bit stream. Refer to the configuration user guide for your device family. Find the size of the bitstream for your density of FPGA. You should also be aware that if your daisy chain contains multiple FPGAs in the configuration scheme, your flash PROM will need to be big enough to contain all the bitstreams in the chain. Likewise, this is a popular configuration for designers that want to load a single FPGA with different bitstreams at different times while their application is still running. This reconfiguration is referred to as multi-boot applications and should be planned sufficiently so you can choose a SPI flash PROM that is sufficiently large enough to accommodate all the additional necessary bit streams. If you're building an embedded application, it is also possible to store your software code in the flash PROM as well. So, likewise, plan on choosing a sufficiently large enough PROM to store your software. Note that the available SPI flash PROMs use a single 3.3 volt supply voltage. All of the FPGA's SPI flash interface signals are within specific I/O banks. Consequently, the supply voltage for the I/O bank must also be 3.3 volts to match the SPI flash PROM. This implies that any I/O pins assigned by the user into the I/O bank must also be 3.3 volt compatible. Spartan 6 is 3.3 volt compatible, however, Vertex 6 is not. This means that if you are targeting Vertex 6, you'll need to build the external interface circuitry. For more information on building this interface circuitry, refer to the Xilinx Solutions database for more information. The majority of SPI flash PROM vendors do not yet build a SPI flash PROM that is compatible with Vertex 6, but check with your vendor for availability. In BPI mode, the FPGA configures from a standard parallel NOR flash PROM. The BPI configuration interface is primarily designed to support standard parallel NOR flash PROMs. The interface supports both Byte-Wide, that is by 8, and Byte-Wide half-word, by 8 and by 16 PROMs. The BPI interface can work with other asynchronous memories that use a smaller SRAM-style interface, such as SRAM, NVRAM, E2PROM, EEPROM, or a masked ROM. As you can see in these cases, no clock is needed because the FPGA contains the control logic. As an FYI, a NAND flash memory is a different technology. FPGAs do not configure directly from NAND flash memories. Note that the flash device can also be used in embedded software applications where it may be necessary to store a system's software in a flash device, as well as the FPGA's bitstream. In an embedded application, such as one targeting the PowerPC or a Microblaze processor application, the platform flash can store the application code, then after configuring the FPGA can transfer the software from the platform flash to an off-chip memory, usually an SDRAM. The software code is then executed from that external SDRAM. FPGAs support two versions of BPI configuration. BPI Up starts configuring the FPGA starting from flash address 0 and automatically increments the memory addresses. This is the most popular mode and most likely the primary mode to be supported in future FPGAs. The other version, called BPI Down, starts configuring the FPGA from the highest memory location and automatically decrements the memory addresses. This addressing flexibility allows the FPGA to share the parallel flash PROM with an external or embedded processor. Depending on the specific processor architecture, the processor will boot either from the top or bottom of the memory location. This allows the user to maximize the use of their flash device by allowing the software code to be stored in the same flash device as the bitstream. Note that BPI down is not supported for Spartan 6 devices. The BPI interface also functions with Xilinx Parallel Flash Platform Flash PROMs, which includes a 128 megabyte device. There are a number of supported NOR flash memories that are currently supported, including mnemonics and spansion. But be sure that you check the configuration user guide for your FPGA's uncompressed bitstream size. This will help you determine which NOR flash PROM is big enough for your bitstream and, if necessary, your design software code. Now let's wrap up this module with a summary. Field programmable gate arrays are usually configured on PowerUp from an external data source. SPI and BPI are the simplest configuration modes and take the least effort to debug. This is because all the configuration control logic is stored inside the FPGA or external memory device. Slave configuration modes take the most effort to debug because they require the user to build their own configuration control logic. JTAG access enables much easier testing and debugging of your prototype and while your system is in production. It is always a good idea to support a JTAG configuration scheme when building your system in case you need to debug your design later, for whatever reason. My first question, should my FPGA load its configuration data from an external memory resource, or should a processor or microcontroller download the configuration data? Well, the benefit of slave configuration modes is that the bitstream can be stored pretty much anywhere in your hardware system. You can store your bitstream on a flash, laptop, hard disk, or somewhere on your network. Your system can basically be whatever you're willing to build. In fact, many customers build their control logic to support in-system delivery of FPGA updates through JTAG as well as support another configuration scheme. While this complicates the construction of the control logic, it does allow debugging the system at any time. The caveat associated with slave configuration schemes is that you'll have to purchase additional components such as a CPU or a memory device. For the control logic construction, debugging slave systems is usually more challenging because you have to build it yourself. Master systems have the added benefit of having the control logic already built inside of the FPGA, so debugging becomes minimal. But regardless of how you choose to load your configuration data, make sure that you consider also supporting JTAG for configuration. This will give a guaranteed way to program the FPGA in case you need to debug your configuration scheme. Should my system use a single FPGA or use multiple FPGAs? Well, most applications only need one FPGA. That's because, of course, the density and the pins for the newer devices is so large. But some require more pins than are available in a single package or more logic than is available in a single FPGA. In those cases, the user should plan on building their application with multiple FPGAs and use a single data source for storing that bitstream. When this is done, a daisy chain always makes the most sense since it reduces the board routing and reduces system cost. You should also remember that every configuration scheme supports the use of daisy chains for configuration. Now, we will be discussing daisy chains in a few minutes. I'll also point out that your configuration user guide will also show more possible daisy chains than we're going to show you in this recorded e-learning. Another common question we'll get is, which is the simplest configuration scheme to debug? Well, master, BPI, and SPI modes are the easiest to debug since their control logic is already included and verified. These modes also have the fewest pins versus parallel modes, which have the most pins to resolve. However, SPI and BPI modes may also be the least expensive of the simple configuration modes. So you might want to read up on all three if you're looking for just the simplest, fastest way to get it done and move on. Should I choose the lowest cost configuration solution? Well, to answer this question, we need to ask a few questions of you. First of all, do you have a spare non-volatile memory component in your system, such as system memory, hard drive, or does your application support downloading a bitstream remotely? If so, then you may want to build your own slave configuration scheme that allows you to store your bitstream in any one of these resources. Another question to ask is, can you consolidate your non-volatile memory required in your application? If so, the compression or consolidation may allow you to purchase a smaller memory component, and that will save you money. Likewise, can your bitstream be stored with your application code? If you're building an embedded design, then you should consider having your embedded application code stored with your FPGA's bitstream. If you're building an embedded system, have you considered using SPI or BPI configuration schemes? If so, then you know they are part of a very competitive marketplace that is one of the least expensive configuration solutions. Another question is the fastest possible configuration time the more important consideration? Well, at the same frequency, parallel configuration schemes are inherently faster than serial modes. Of course, if you're configuring multiple FPGAs in a daisy chain, then your configuration time will be no longer. But there are a few things a user can do to speed up their configuration time. In a master configuration schemes, the configuration clock frequency can be increased. However, how much it can be increased will depend on the read specifications of the non-volatile memory component you're using. So if you can purchase a faster memory component, you may be able to increase your configuration speed. Likewise, since your FPGA's configuration clock will vary by speed grade, you should be able to increase your configuration speed by using a higher speed grade FPGA. If you have an external clock in your system that is faster, you may be able to configure it in a slave configuration scheme at a higher clock rate that way. As an FYI, note that if you want to configure an FPGA at a higher rate, you should take care to avoid any signal integrity issues. Many customers do not bother with this, and they end up having to debug their configuration process later on. Another question is, will the FPGA be loaded from a single configuration image or with multiple images? Well, if your application needs multiple images, there are some nice FPGA features to consider. The solution to this problem exists in Xilinx's newest FPGA families and is called multi-boot. This allows an FPGA to configure with different bit streams on whatever occasion the designer would like. One of the best examples of this is during a hardware-assisted test. In this scenario, the FPGA is loaded with a bit stream to perform the self-test, followed by another bit stream with the final application. The JTAG and slave configuration schemes are frequently used during debugging for this purpose just as well. Another frequently asked question is, what I/O voltages are required in the end application? Another common situation arises when a designer is planning on operating their FPGA at a voltage other than 3.3 volts. When this happens, the user needs to be aware that the memory component they may be interfacing to may require a voltage other than 3.3 volts. In this case, it is important that the designer be aware that the FPGA configuration pins are reserved and usually placed in a single I/O bank. Thus, depending on your configuration mode, that will require all the I/O pins in that bank to be compatible with a 3.3 volt device and may limit where you want to place your other I/O pins on your FPGA. So plan your use of the bank pins associated with your dedicated configuration pins. Plan them a little carefully. The most common scenario customers are encountering is that the Vertex 6 is powered at 2.5 volts and needs to interface to a 3.3 volt SPI or BPI component. If that is the case with your design, you may want to consider using a Xilinx platform flash PROM. Also remember that other vendors are eventually going to be producing a compatible flash memory. So check the vendors you see listed here in this slide if you're using a SPI or BPI configuration mode for Vertex 6 if you don't want to use a Xilinx platform flash device. Should the FPGA's I/O pins be pulled high via resistors during configuration? Well, it's important for all users to be aware that floating signal levels can be a problem in CMOS logic systems. The internal pull-up resistors included with each I/O pin generates a logic high level on each pin, and most customers use them so their signal levels don't float. Floating signals levels are a problem in CMOS systems and should be dealt with by the designer, but the use of the pull-up resistor is optional. If necessary, the designer can add an external pull-down resistor. Some customers choose to turn off the use of the pull-up resistors because it provides a current path to the I/O power rail in hot swap applications. But the caveat to this is that an external pull-up or pull-down resistor is then required on each I/O pin at some additional cost and effort to the user. Another common question is, does the application target a specific FPGA density, or should it support migrating to other FPGA densities in the same package footprint? Some customers are unaware that the package footprints and pinouts of some Xilinx device families are designed to allow migration between different densities within a specific device family. This is important because if the user is planning on purchasing a memory device in advance, you may need to consider selecting a memory device that has sufficient size to target the largest of those chosen FPGA family densities. So for example, the Spartan 6 LX FPGAs support identical package footprints when using the 256 ball fine pitch thin ball grid array package. The Spartan 6 SLX4 device requires 2.5 megabits of storage to hold its bitstream. The largest device in the same family and package is the Spartan 6 SLX150, and it requires just over 32 megabits. If the user wasn't sure which density he would need, he should allow sufficient configuration memory to cover the largest possible density. Don't forget to include the size of any software that you may also be planning to store in your memory device as well. This will allow you to make sure that you anticipate the worst case scenario for both your software as well as your bitstream size. Okay, now that we've got some frequently asked questions out of the way, maybe that's served to help review some of the stuff you learned in the first REL, and we've taken our first quiz. Now we want to take this module into some of the deeper topics that maybe we didn't have a chance to cover in part 1, as well as get into some more advanced topics and advanced questions that people might have. So, well, first we want to mention that there are a couple of utilities included with the ISC software that many people use, and it's pretty helpful to understand their role in the development process at this point as we continue on with our discussions. First of all, BitGen is used to make your bitstream. Of course, this can only be completed after the design has finished implementation, which means that a finished design has been made by the implementation tools and a correct NCD file is available and has been completed. As you will see, the NCD file contains everything about your finished design. That means it is a required input to the FPGA editor, which is one of the utilities in the ISC tools, and is used to understand the design in gross detail. Likewise, the NCD is an input to the chip scope, which is used to debug a design, as well as various other reporting utilities, even the plan ahead software if you want to control layout. So the NCD file is really everything about your finished design. It's a very key file because it's used as an input to so many other analysis utilities. Now, as you can see from this diagram, once the NCD file is made, BitGen creates the bitstream used for programming the FPGA. This file is given the .bit extension in case you're looking for it or want to make sure you archive it. Impact can be used for generating PROM files, which uses the bit file as an input. Impact also can be used for configuring your FPGA in system directly from a host with a download cable. Xilinx recommends you use either of the latest platform USB cables. We'll have a chance to talk a bit more about those cables in a few slides. The third utility I want to talk about is the PROMGen utility. It's used to generate a wide range of PROM files. Supported files include the MCS86 from Intel, the XORMAX from Motorola, and the TechHex from Tektronix. This utility can also make binary and hexadecimal files for other PROM vendors. These are the primary prototyping cables that Xilinx offers. The platform cables are the most popular cables. Both the platform USB and the USB 2 cables attached to your computer's USB port and can be used to configure Xilinx FPGAs, as well as program Xilinx CPLDs and PROMs. They are serial download cables and support downloading designs with the Impact utility and debugging with the ChipScope Pro Analyzer, as well as other utilities. But note that the big difference between the two platform cables is that the USB 2 cable supports programming SPI flash memory devices as well. The parallel cable is also a serial download cable and supports clock rates of up to 5 MHz. The parallel cable, commonly called the P4 cable, attaches to your PC's parallel port and is the slowest of the serial download cables. Xilinx recommends that users plan on using the newest platform cables, that's the USB 2 cable, if possible. The platform costs around $150. You should note from this slide that the platform cable can be used to download bit streams in JTAG and slave serial configuration modes as well. Finally, please note that the Xilinx cable hardware is not recommended for production programming. Now we want to spend a few slides and a few minutes discussing the configuration process. And the first thing I want to point out is, again, that understanding this completely is not as critical as you might think. There's a few of the steps that is relevant sometimes when you're trying to debug a slave configuration scheme that you've planned out. But beyond that, a lot of this is, again, embedded in the FPGA and done automatically. And either you get to this point in the configuration and configuration finishes off, but there's only so far that you can debug. So really your key thing here you're trying to understand is what are the key signals, what is their behavior during the configuration process, so that if I'm trying to debug my own slave configuration scheme, I can do so. Now the configuration process is going to be described again in the next few slides. Our goal here is for you to get a rough idea about how this whole process fits together. And again, generally designers don't need to understand it, but isn't it funny? They want to know this anyway oftentimes, especially if they're building their own slave configuration scheme. Xilinx is certainly not opposed to designers building a custom scheme. In fact, it's often essential, and that's, again, one of the reasons why we're trying to cover it here. Configuration is broken into three main steps: setup, loading, and startup, as you can see from this diagram going left to right. There are 8 individual steps that further break up these three processes. That is the device power-up, the clear configuration memory, sample mode pins, synchronization, do a device ID check, load the configuration data, complete the CRC check, and then finally allow the startup sequence. The first step is power-up. As you can see from the diagram, the device has to power up with the VCC internal rising sufficiently. The rise time will vary by device, and we encourage you to review your device documentation to find out your device's particular needs. But this is probably the #1 mistake users make: insufficient rise time. If the rise time is insufficient, you can expect the FPGA to never look like it has configured, which means that, of course, the done pin will never go high. Of course, other configuration signals won't register properly either, but this is the first thing to always verify. After the FPGA powers up, the init pin is released and gets pulled up by an external pull-up that you must provide. After a little bit of time, the configuration clock, that is the C clock, will become available if a master configuration scheme is being used in this case. Step 2 is simply to clear the configuration memory. And again, this is pretty much automatic. This is done automatically with configuration or can be forced by the user when the program pin is pulled low. After it is activated, the memory is cleared twice, and the I/O pins are placed in a high Z state. During the clearing stage, a NIT is pulled, and as I mentioned in the previous slide, and then released after the second clear. If a user wants to delay configuration, this can be accomplished at this point by holding the init pin low externally. This is very commonly done by users building their slave configuration scheme, or as I mentioned, combining multiple configuration schemes. Once the init pin is released and goes high, the FPGA samples its mode pins, and the configuration clock begins to run. Step 4 is the synchronization process that aligns the configuration data with the internal configuration logic that is a part of the FPGA. This is probably the first phase that you really don't need to understand, because at this point you have either set up your external control logic and the FPGA has configured this far, or you blew it and you're busy debugging your configuration scheme that you may have customized. Now, after synchronization, the FPGA checks your device ID. This is, of course, a necessary security measure. If it fails, then fallback reconfiguration can occur. We'll talk a little bit more about fallback configuration a little later. The CRC, or checksum, as it has been commonly been known, is used to verify that the bitstream has not been corrupted. It compares the downloaded code with its calculated value. If it does not match, configuration is aborted and the init is pulled low. What is most important to remember is that if you need to debug your configuration scheme, you will need to verify key points along this process, and one of the most critical is when the init goes low again. This is important because customers frequently have board level or prototype issues that do not allow the bitstream to be transmitted from a flash to the FPGA properly, and they wonder why a nit is pulled low. Well, now you know why. Now this diagram provides you with a nice graphical display of the whole configuration process from beginning to end. In our case, we're down at the startup region in the far right of the diagram. Startup contains several useful services that most customers appreciate. These include wait for DCMs to lock, which is optional, wait for the DCI to match, which is also optional, negate the global 3 state, that is the GTS, which activates the I/O pins, release the done pin, this is an open drain output requiring external pull-up, assert the global write enable, allowing the RAMs and flip-flops to change state, and then asserts the end of startup, or EOS. Note that the last 4 steps we've just listed, that is, are the default. The most important step here is the release of the done pin. This is, of course, the final confirmation the configuration worked properly. Note that it also needs an external pull-up resistor. In fact, I encourage you now to double-check with your configuration user guide that you have sufficient pull-up resistance on your critical configuration pins. This is also a very common mistake designers will make. Many customers have told us that when it comes to their preferred training experience, they want to be challenged a little bit. Well, we're about to challenge you. This next example is about daisy chaining. I want to first note that this is not the only daisy chain you can build. You can learn more about other daisy chain configurations from your device family's configuration user guide. But for now, we want to introduce the concept because daisy chains are used to manage your configuration resources, and daisy chains help you minimize your board traces and minimize the number of prompts your system will require. So if you don't recall the basic signal definitions we mentioned in the basic FPGA Configuration 1 REL, you may want to refer to your printed copy of that module to answer the questions. Or you could simply refer to the configuration user guide available on our webpage at support.xilinx.com and look at these signal definitions there. But with a little bit of extra effort, you should be able to complete our daisy chain in this next example we're going to show you. But first, we want to recall that the first FPGA in the chain to be configured can be in any configuration mode, unlike other devices in the chain, which must be in the slave mode. You should also note that besides the basic chain we're going to show you on the next slide, other modes support chains. We're just going to start with something basic so you can get a grip on things. So in our first example, the Xilinx Platform Flash PROM is on the left of the system. It is connected to the middle device, which is a Virtex 6 FPGA. The first device has its mode pins all tied to ground. First thing we should ask you is, can you tell me which configuration mode this is in? Well, you should go to the user guide and you can review, or go back to the first REL and review, but yes, it's in master serial mode. Now recall that the first device in the chain must be in master serial mode. You could have found this out from the user guide, or remember that I mentioned it earlier. Each configuration mode has its own unique mode pin combinations. In master serial, all mode pins are tied low. In slave serial, all mode pins are tied high. Note, this can differ by device family, as we'll see when we look at the Spartan 6 version of a daisy chain. Note the connections of each pin in this diagram. We first have to connect the FPGA's clock and program pins to the corresponding pins on the FPGA. The clock pins are tied so the configuration is synchronous to one clock. The program pins are all connected so that the entire system is reprogrammed on command by the user. There's no point in reconfiguring one device. You've got to reconfigure the whole system. In this simple example, it's not possible to reprogram one FPGA without reprogramming the others in the chain. Since this is a serial daisy chain, the data from the PROM goes to the first FPGA, that's the device in the middle, and then the data out pin from the first FPGA will connect to the second FPGA to its data input pin, and so on if there are more FPGAs in the system. This assures that the first FPGA will be programmed to completion before passing the bitstream to the next device without corrupting the bitstream. We also have connected the init pins together. Tying the init pins together allows for error checking the entire system since they are all tied together. If one is clearing, the node is pulled low and configuration of the system is not allowed to continue until all the FPGAs have been cleared. Then the node can be pulled high by the resistor. Likewise, later when the FPGA is loading its bitstream, a nit can go low on any one of the FPGAs, indicating that the bitstream has failed its CRC check and the configuration is being aborted. We have also connected the done pins together. Tying the done pins together prevents the system from coming out of configuration until all of the FPGAs are configured properly. Note that you should check your configuration user guide and the datasheet to determine the proper pull-up resistors necessary for this kind of system. Now, conceptually, configuring a serial daisy chain is really no different for Spartan 6. However, there are only two configuration mode pins. In this case, master serial is given the combination 0-1. That is that first device in the middle, while a second device is configured in slave serial and is given the combination 1-1. Now, likewise, when you go back to the Vertex 6 diagram, you'll note that the second device, being in slave serial, now has a different configuration setting on its mode pins than the middle device, which was in the master device. So, again, just double check that, make sure you got your devices with the proper mode voltages for your device family. So to review, connect your program pins together. This is required, so all FPGAs will reprogram together. Connect all the clock pins together. This is required, so all FPGAs are synchronized with each other and with the data stream. Connect each data out to the data in of the next device. This is required to allow each FPGA to receive the data stream. Connect the init pins together. This will create a single error flag. Connect the done pins together. This will create a single status flag. And connect the done to the chip enable input of your PROM. As an FYI, check your clock termination and the specifications for the clock signal with the user guide. Again, many customers create problems for themselves when they do not meet their configuration clock requirements. This is probably one of the most frequent technical issues customers experience. They simply do not have a sufficient configuration clock, and the done pin never goes high, and they're not sure why. So now we just wanted to explain a little bit more about how all this works. So the way it works is that a synchronization word is passed to each device. The synchronization word is used to alert the FPGA that configuration data is coming, and it should prepare to receive the data. After the first FPGA is synchronized, it is programmed. During the first device's configuration, it keeps the data out pin high until it is completely programmed. Then data is passed to the next device in the chain in the same manner. After all the devices are programmed, the done pins on all the devices are released and pulled high. This done signal is used by most designers as a trigger to start the startup sequence of their system. The Platform Flash product is used by many Xilinx customers. It has large densities, 8, 16, and 32 megabits, and supports many Xilinx FPGAs. That is, all but the largest and the very newest FPGAs. It supports many configuration modes and is in-system programmable. It also is internally powered at 1.8 volts. It also has a data compression feature that allows the user to target a smaller density platform flash. In fact, 100% of designs tested had their bit streams compressed by at least a third of their size. The platform flash also supports a new slave serial mode where the configuration clock can be made from the platform flash as well. The platform flash also has a design revision functionality that allows the user to select between 4 unique bit streams. This enables the user to program their FPGA from any of their design revisions. Now, this is especially useful for building testing systems in which the user plans to run a test of their system each time after power occurs, then reprogram the FPGA with a specific bit stream after the test is completed successfully. This revisioning functionality is being used by customers for safe updates, where, say, for example, Rev 0 would be the golden or proven image, and Rev 1 and Rev 2 could be the new updates. Revisioning allows the golden image to be used in cases where the new image will fail for whatever reason. System tests can also be done with revisioning. Rev 0 will be the board test configuration, and Rev 1 would be the production version. This allows the system to automatically reconfigure the FPGA with a production version after passing the board test. The newest platform flash is the XL. It's designed to work with the newest configuration modes. The XL has up to 128 megabits of in-system programmable flash storage. It also has a NOR flash interface that allows users to store not only their FPGA bitstream, but their software code or use the extra memory space for extra data storage. Parallel NOR flash devices are advantageous over other configuration memory sources when large storage density, that is, density over 128 megabits, or fast configuration speed is required for your application. This makes it an extremely flexible device for embedded and other high-density applications. In the diagram on the left, we see the data connection between the FPGA and the XL being used to transfer embedded code or data from the flash to the user-designed program into the FPGA. The XL is designed to work with the master SelectMAP mode. This has a wide 16-bit data bus that delivers the FPGA configuration bit stream at speeds up to 30 MHz, corresponding to 800 megabits per second. This allows it to program the Virtex 5 LX130 device, which is one of the largest densities, in less than 85 milliseconds. This makes it the fastest configuration solution for Xilinx's newest FPGAs and ideal for FPGA endpoint solutions for PCI Express and other high-performance applications that require fast configuration times. The XL also has a power-on-burst read mode and dedicated I/O power supply, which enables the Platform Flash XL to mate seamlessly with the native SelectMAP configuration interface. The Platform Flash XL also supports indirect programming of the flash with a single cable. In this diagram, we see the JTAG connector being fed the data for programming the Flash XL. This data is then passed through the FPGA, through the BPI flash configuration port, and finally used to program the Flash XL device. Note that special control of the power supply sequence or delay of the configuration process can be required to ensure power-on readiness of the XL before the BPI address sequencing. Configuration of the FPGA with the Platform Flash XL can also be completed with Master BPI Up, Slave SelectMAP, or Master SelectMAP configuration modes. Reconfiguration for fallback can occur when an error during configuration occurs and the user wants to have a safe bitstream used for configuration in a backup memory or emergency situation. This same idea was discussed earlier with the original Platform Flash device and was referred to as revisioning. Well, this simply applies here as well. Warm booting occurs when a designer might want to change the image stored in the FPGA without powering down the FPGA, which would be the normal way people might reconfigure the device. Multi-boot is most commonly used for storing a golden image on a flash device as a fallback image when a user is either testing a new update to a design or wants to run a test of their system each time after power-up occurs. With multi-boot in Virtex 6, 2 bits are used to communicate with the Platform Flash XL, which image is used to be loaded into the FPGA. These bits then select whether the fallback image or another image will be loaded. Note that this reconfiguration, or warm boot, can also occur anytime a user wishes without powering the FPGA down. Similar functionality can be accomplished with Spartan 6, but it is different. But the main difference is that the reconfiguration cannot be activated by external pins. That is, that there are no RS output pins from the FPGA. In this case, a series of ordered bit streams are stored on the flash device, and the configuration logic is designed to automatically go to the golden image when an error during configuration occurs. Now, I really would encourage you to read up on this. We've barely touched on it here in the differences. So for more information, refer to the Spartan 6 configuration user guide. Now, let's take a few more minutes for one last short quiz so you can see how much you've learned from this REL. Now, let's wrap up this module with a summary. Field programmable gate arrays are usually configured on power-up from an external data source, and this data is more commonly being stored in flash devices that support the newest configuration schemes, that is, SPI and BPI modes, are the simplest configuration modes and take the least effort to debug. Slave configuration modes take the most effort to debug because they require the user to build their own configuration control logic. JTAG access enables much easier testing and debugging of your prototype and while your system is in production. It is always a good idea to support a JTAG configuration scheme when building your system in case you need to debug your design later. Multiple FPGAs can be connected to form a configuration daisy chain. This allows designers to program multiple FPGAs from a single flash component. The platform Flash XL is designed to support Xilinx's newest and largest FPGA families. It also includes a NOR flash interface that allows designers to store data and software with the FPGA's bitstream in a single flash component. Likewise, the platform Flash XL offers the fastest FPGA configuration rate through master SelectMAP mode. This makes the XL ideal for PCI Express and other high-end performance applications. There are some very useful resources available to you on support.xilinx.com. And to help you learn more about these device configuration schemes, go to our website. It's support.xilinx.com, of course. Or from the ISE software, just click on Help and select Xilinx on the web and select a device family from there. From here, you should see various documentation categories. Then select Configuration User Guide. These documents will provide even more detailed information about all the topics we've covered here. As you can see, every one of our device families has its own configuration user guide. To learn more about the Xilinx Platform Flash XL device and its supported configuration modes, refer to its user guide, which can be accessed from the same location. To learn more about the roles of Impact, PromGen, and BitGen, review their sections in the Command Line Tool User Guide, which can be accessed from the website or directly from the ISE software, just as I showed you before. There's also more information available about the platform cable USB 2. It has its own user guide and datasheet. We want to mention that the installation guide, that is, User Guide 344, has additional information about troubleshooting its setup. So if you use this cable, and many users do, be sure to download this document in case you have some difficulties. If you would like to evaluate BPI programming from the ML65 or Spartan 601 demo boards, there is a tutorial that is available on the Evaluation Kit page. It will give you practice preparing and setting up for configuration targeting both of these new demo boards. You should also check out the Configuration Problem Solver. This utility walks you through the configuration debugging process and helps customers debug their own configuration problems. While this utility is very helpful, we don't want to discourage any of our customers from contacting the hotline or submitting a web case with their configuration concerns and questions. We just find that many customers would rather help themselves rather than being on hold or making a phone call. So give it a try and let us know if you have any questions. If you would like to see what other courses we offer or what other free recorded e-learnings are available, go to the Xilinx Education link you see here. I'd also like to mention again that there are architecture modules available that discuss the basics of Xilinx's newest devices. You may find this useful, especially if you want to learn more about these device differences. But whatever you do, please take a second and let us know what you think of this REL. Just click on the icon on the next page and tell us what you thought. And again, we really recommend this because, of course, we get more feedback, positive and negative, than, of course, resources or more time and effort are assigned to these projects. Now, again, my name is Frank Nelson. Thank you very much for listening. You've been listening to the Basic FPGA Configuration Recorded Learning Part 2. Again, thanks for listening and thanks for your business.